Professor Samin. She's from the University of Technology in Malaysia. And the topic will be some results on topological indices of graphs associated to groups and rings. Okay, the floor is for you, Prof. You can start.
Thank you to the chairman. Assalamualaikum and good afternoon from Malaysia to all. First, I would like to thank the scientific committee and the organizer, Prof. Ahmad Irfanian, and the host. I'm really sorry I couldn't be there. I planned to come, but also the same with my students. I hope the next BIGTC would be able to come. My sharing today is some results on topological indices associated to groups and rings. And this is joint work with my former PhD student, Nori Dayu, and my student right now, Ghazali, is doing part of his research on this topic. My presentation outline is as follows. I will introduce a little bit about the motivation, what are the topological indices, and also we have seen some graph associated to groups, including non-commuting graph. I'll just briefly share the definition. And we also have graph associated to ring, and we will see today some results found on the topological indices of graphs associated to these groups and rings. We see a little bit application on molecular structure at the end, and followed by conclusion and our research recommendation. So why are we doing and why are we computing these topological indices? So topological indices provide numerical descriptors that capture important structure features of molecules. So you can see the 3D representation of molecules on the left, and they are in the form of graph. You can model as graph, and it's a mixed graph with a two-dimensional representation. So they serve as powerful tools for analysis and prediction of various physicochemical properties and biological activities. This has been doing by mostly biologists and chemists. And the significance of topological indices lie in their ability to transform complex molecular structures into numerical representation. So this enables the development of computational models and also efficient exploration of chemical space for various applications. We see many papers on drug discovery, on material science, and reaction chemistry. In some of them are stated in this paper by Goodman and Polanski. Now, various types of topological indices have been developed based on either chemistry or mathematical perspectives. And this research is been done by also some participants here that I will mention the paper later. And we also discussed this with the chemists in UTM specifically, and they are looking forward to see the results by the computation theoretically, because they have to go to the lab and it will cost more and more timely. So some of the topological indices that I will be sharing this afternoon or still morning there, it's Wiener Index, Zagreb Index, Rendick Index, Harari Index, Zagreb Index, General Zeroth Order Rendick Index, and very recently Sombo Index. So these are the different types of topological indices. Let me go through the definition of each of these topological indices. Then you will see how we can use the properties of the graph to calculate these indices. So the first type of this index had been discovered by Wiener in 1947, in which the Wiener number considered the path of a graph. And they first calculate this for some paraffins, and they tried to find the boiling points of these paraffins. In Hosoya in 1971, find the formula of the Wiener index, and they call it a winner, the winner number as winner index. And this is the formula. It's the sum, the double sum of the distance of each of the vertices I and j, and up to the total number of vertices in the graph. Just a simple example. You've seen this graph before, the non-commuting graph for D6, in which we have an edges. If they don't commute, and the one that commute A and A squared, there's no edge there. So you can see the distance just in between A and A squared will be 2. The others, they are all adjacent, so it's 1. So we calculate all possibilities of this distance in between 2 vertices, and we get the number to be 11. Next, we will use this a lot, so I just put it here first. In 2011, Azad and Eliassi found the winner index in the form of the order of G, the order of the center, and the conjugacy, number of conjugacy classes. This is very interesting. If G is a finite group and gamma is the non-commuting graph, then the winner index of the non-commuting graph is given by this formula. Half of the product of, you can see the order of G, subtracting the center, which has something to do with the definition of the commuting graph, and also the conjugacy classes. So you need to find the number of conjugacy classes and also the center of the graph. For the Zagreb index in 1972, Goodman and Trinastic introduced the degree base. Just now we see the distance base. Now we use the degree base. And it's divided into 2 types, the first Zagreb index and the second Zagreb index. So the first Zagreb index is the sum of all the vertices in the set of the degree squared. For the second Zagreb index, it's the product of degree of 2 vertices in which they are adjacent, u, v in the edge set of edges of the graph. So based on this graph, you see that the degree is the number of edges connected to that vertices, right? You have all the degree 3 and 4, and we just square those degree and add them up, and we get the first Zagreb index. While the second Zagreb index, you multiply each of the UV, which are adjacent. So except for these 2, the others we just multiply, and you get the second Zagreb index. For the Zagreb index, we also have a property for specifically non-commuting graph, in which you don't have to use the definition or multiplying the degree or finding the degree squared and sum all of them. If G is a finite group and we have the non-commuting graph of G, then the first Zagreb index can be calculated using this formula. So you just find the order of G, you square, then you multiply that, and you add up the order of the center, and then you subtract twice of the conjugacy class number. And then you also have to find the order of the centralizer for each element not in the center, and you have to square that. And this is found by Mizagar and Ashrafi in 2012. And they also found the formula for the second Zagreb index of the non-commuting graph of G. The next one is the Zagreb index. This is a little bit more complicated than the others. If you have a simple connected graph and you have this vertex set, 1 through n, then the Zagreb index is given as the sum of the product of the n1 and n2. So what does it mean? This is what we call the summation embraces all edges. So the n1 is the number of all those elements v in which the distance, you see the distance between the vertices with the x is less than the vertices with the y, if v is xy. And n2 is the other way around. So you only count the vertices that are closer to one edge's terminal than the other, and the other one is vice versa. And let me show an example for that, a simple connected graph. So let's say capital N1 is the set and we find small n1 to be the order, and n1 EI is the vertices lying closer to one endpoint X of the edge EI than to the other point. So you see, suppose we take the edges 1, 2, this 1, 2. So you have 1, 2, 3, 4, 5 edges. We have to calculate this 5 times. So for the 1, 2, you find X in which the distance X with this one is less than that distance X with this 2. And of course, the smallest one will be the distance from X to X. So we have 1 in there. And then we have another one, which is 4, which is because the distance of 4 is 1 to 1 and 2 to 2. So that is the set. And we calculate the number, which is 2. The other one is N2, the same set 1, 2. So you find with 1 and 2, the other way around. So to be more than, meaning the 2 has to be in there, and for that's the only one. So we calculate this for all the other edges, and we get for the second edge, the third edge, you look at on the right, that is the number that we want, and all of the edges, then we can find the Zeiger index of this graph, which is the sum of the product of all those numbers that we found. The next index is the Harari index, and the Harari index is what we use as the matrix. First, we look at what is the matrix DR. We call this matrix is the reciprocal of the distance. And the Dij is the shortest distance between the vertex. So you find the shortest distance, you take the reciprocal, and depending on whether I is j, you take the sum, and you take half of those. So this is the Harari index based on the same graph. So you take all possible distance in between the two vertices, and you take the reciprocal, and you sum up, and that is the Harari index. Okay. Next is the Randic index. It's a graph theoretical descriptor that quantifies the complexity or branching structure of a molecular graph. And this is, the name is the person who introduced that, which is Milan Randic in 1975. And he found various applications in various fields in chemistry. And the Randic index is defined to be the sum of the reciprocal of the square root of the product of the degree. So you will get non-integer numbers as the answer. So based on that figure, we find the degree, and then you just take the product and square root and take the reciprocal and add up all of those. So we get 2.48. General zeroth order Randic index is modified from the Randic index, and it's defined to be the sum of the degree to the power of alpha. And this alpha can be non-zero real number. And this index has been introduced by Ahmad et al. In 2019. And very, very recently, in 2021, a new topological index, which is Somboid index, has been established, and is defined as the square root of the degree squared plus for the edges, for the vertices of the edges. Now, based on the figure before, we can calculate this similarly as before. Now, we have heard this from, I think, the very first day, the non-commuting graph. I was looking for, actually, Professor Abdullahi. I didn't see him. I'm not sure if he's there, but he introduced this non-commuting graph of a group in 2006, in which the vertices are all elements of the group, minus the center, right? You don't want the center to be because it's non-commuting. And we join the edges in whenever the vertices, they don't commute. Okay. And we see some researchers found the non-commuting graph for some groups. For example, in 2018, That's the non-commuting graph of the hydrogen group to be the multipartite graph. And this is separated when the case n is odd or n is even, in which the order of the dihedral is 2n. Next is the generalized quaternion group, and the non-commuting graph is given here. So this is what we were looking for, the topological indices. And the third one is quasi-dihedral group, and this is also the non-commuting graph of the group. Now, our next graph that we are interested to find the topological indices is called the co-prime graph, in which a co-prime graph introduced by Ma and all in 2014 is a graph that the vertices are all elements of G and two distinct vertices are adjacent if the order of the vertices, they are co-prime. As an example, in D8, we know that D8 has order 8, and so the all elements divides 8. So 1, 2, 4, and 8, and 1 to 4. So the order are not co-prime. That's why we have a star graph. We have only 1 and 2. So 2 and 4 and others, they are not co-prime. In 2014, Ma generalized the co-prime graph for certain order of dihedral groups. So we can see that for dihedral groups of order 2n, the co-prime graph is a multipartite graph if n is odd. And he found that it's a star graph if n is a power of 2 for some positive integer k. And with these facts, I will show you the topological indices at that graph. Our next graph is associated to rings. We are also interested to see some graph associated to rings. And in 1999, this graph was introduced by Anderson and Livingston, called a zero divisor graph. So we have a commutative ring with identity. We have the set of zero divisors. We did not exact of R. And the zero divisor graph is this graph. Well, there are two different definitions of zero divisor graph. One is that the edges are all the non-zero zero divisors. And there's another one in which the vertices are all elements of the group G. But the one that we have is the vertices are the non-zero zero divisors. And two vertices A and B are adjacent if the product is 0. AB or BA is 0. So for example of Z27, you cannot really see, but these are the zero divisors, which is non-zero. And we have the product of those two, whether it's 0, you will have adjacent. Now, let's look at the topological indices of these graphs. The winner index of the non-commuting graph for these three groups. So for the first one is for the dihedral groups, in which the one that I've shown before, this is the winner index, using the definition of the winner index to be this polynomial. Okay, and this results is found by Noridayu in 2021. And we work together also with Prof. Irfanian in finding this. And we also started with the definition, but then we use the fact that we have the properties using this formula that I shared before for the winner index. So we use this formula to just put in using the properties of the groups just now, because there's also results on the conjugacy classes of the dihedral groups. So this is for n odd and another one for n to be even. Next is the winner index for non-commuting graph for these other groups, which is the generalized quaternion group Q for n of order 4n. And this is the winner index. Okay. Also polynomials of degree 2. The next one is for quasi-dihedral group for order 2 to the n. And we found the winner index. You can refer to paper. This is from my former PhD student, Nur Idayu, working together with Professor Ahmad. The next one is the winner index of the co-prime graph for some finite groups. So this is limited to n odd, and n is 2 to the k, because the open problems for the other cases, since we cannot generalize the co-prime graph for the case other than the even n. For theorem 4, the winner index of the co-prime graph is given in the following. Using the fact that the winner index can be calculated using the property before. So let me just share a little bit of the idea of the proof. So we calculate when the case n is odd, the graph is the multipartite graph. Then the total number of vertices, we can calculate that as 2n. And they have 3 independent sets. And we have the number of edges. And the number of edges of a complete graph, subtract that with the number of edges of the other 2 complete graph. You get the number of edges. But for this one, we use the definition of the winner index. And we get the double sum of the distance in between 2 vertices. For dihedral groups for the other case, this is the winner index of the co-prime graph using the definitions as earlier. The next one is for the generalized quaternion. If needed, I can share also the slides so you can see the references or the papers. This is published in 2020 and 2021. And for the generalized quaternion group of order 4n with this condition, this is the winner index, 4n minus 1 squared. For quasi-dihedral group, we computed the winner index. Next one is the Zagreb index of the non-commuting graph. This is the cases in which n is odd and n is even. So we calculate the first Zagreb index using the property found before, the one that I shared earlier, which is to find the order, the center, the conjugacy class, and also the centralizer of each x as the vertices, as in G, not in the center. For the case n is odd, and for the case n is even. So we found the first Zagreb index. And for the second Zagreb index, for the same graph, for dihedral group, we found it to be these polynomials. Next one is for the generalized quaternion group, also for the first Zagreb index and the second Zagreb index. And that result has been published in 2018 and 2020. For quasi-dihedral group, because of the order of the groups and the graph it's not just a polynomial like before. It's a little bit complicated, of a power of 2, but they are all depend on n for the first Zagreb index and the second Zagreb index. For the Zagreb index of the non-commuting graph for the hydrogen group, I have this result. And using the non-commuting graph as the multipartite graph for the case odd and even, we calculate the number of edges. And if you remember, the complicated set that we have to figure out, depending on the distance, whether they're closer than one vertex or they're closer than the other vertex. So we use that fact and we find the Zagreb index for this graph. For the case n is even, and by the definition, we come to this answer. For the non-commuting graph for the other two groups, we also found the Zagreb index using the definition. Next is for co-prime graph for the three groups. These are also the result of the Zagreb index. First, for the case odd prime for the group, and we have for the co-prime graph, it depends on the co-prime graph given and found before. For these two other groups, generalized quaternion groups and also quasi-dada groups. Okay, and for the Harari index, also for the non-commuting graph, this is the Harari index. And the Harari index of the non-commuting graph, where n is odd, is half of the total of all entries of the distance matrix. Remember the definition that we have to find the distance matrix and find whether if they're vertices and they're adjacent to each other, then we can use the formula. And also for n is odd. So we arrive to the result. The Harari index of the other two groups is also found based on the non-commuting graph before. Next is the Randic index of the non-commuting graph for those groups. So it's all the square root, but this really matters to the chemists because this is how they calculate and they decide the Randic index for some molecular structure. And this is just submitted to a journal, this result. And the Randic index of the other finite groups, also in review. The last one is the Sombo index. This is our work with Dr. Sanhan from Iraq. I think Dr. Sanhan is here. For the non-commuting graph for some finite groups, we did this for dada groups and for generalized quaternion groups, also for quasi-dada groups. So these are results. I want to share a little bit, just one, associated to rings, in which the first Zagreb index for the zero divisor graph looks like this. All depending on, this is only for Z P to the K. So this is just still the ongoing work by our student Ghazali. And the general zero order Randic index, this is found as below. Next, let me just stop that for just a few seconds. And as I mentioned, this is still ongoing work, and there are a lot other graphs associated to rings. I see some of the students, the PhD students, or probably we can work together on those topics. We look at how we can apply these indices of the point groups. We look at bromine pentafluoride. For this has rotation axis of order 4 and 4 vertical planes, so we can actually map these to the group order 8. They are isomorphic, so we can do the isomorphism property, and we can actually find the Wiener index for the graph that we match up with the molecular structure. So as a conclusion, I have shared many results on the topological indices, the Wiener index, Zagreb index, Zagat index, Hariri index, Randic index, Sombo index, I missed that. There are many other indices that are very interesting in chemistry that we can look at. And based on the results, of course, because it depends on n, and some of them are polynomials, so the higher the value of the topological indices, give the higher order, give the higher value. And chemistry can predict actually, and biology's chemical and physical properties of the molecules using our mathematical model. I recommend that probably I mentioned about some more topological indices, and we can also find some other graphs for rings. And also this very new that we found this paper on chemical structures in drugs, where they're looking for the physiochemical properties and biological activities. So these are just some references that I have shared in my presentation. I wish to acknowledge the Ministry of Higher Education for the grants. Unfortunately, they don't have enough for the flight to go to South Africa. I hope I get more grants for next time. Thank you very much, and thank you for your attention.
Okay, thank you very much, Prof. Salman. Is there any question from the online audience?
Yes, I have one question.
Yes.
Okay, Prof.
Can you hear me?
Yes.
Why you only consider dihedral group or generalized quaternion group? What about symmetric group, alternative? They don't appear in the chemistry?
Well, this is just some results that we share, Prof. We can also do that. There is more work that we can do. For other, it's not that you don't have that for the others. We can do other groups, but this is the one.
It's very important to look at the symmetric group, alternative group.
Yes.
And
There are
general
also
linear
some
group
work
in general, because those are.
Yes.
Okay.
Okay, then thank you, Prof. Muri. Any other questions from the online audience? Okay, don't see. Any questions from the visual audience? Yes, Prof. We can continue.
Prof. Ahmad can also answer some questions.
Okay, can you come
from there? I cannot hear the question.
Okay. Okay.
This is microphone. Yes.
Was I close here? Oh, we can.
It's an active microphone.
Okay. Please stop. Turn off the microphone. Yes. Okay. Thank you for your presentation. You speak about some topological indices. As you know, we have many topological indices, which you obtain only some of them in your presentation. But as you know, also some years ago, I worked in these topological indices and obtained some results on the molecular graph, not non-commuting graph related to some finite groups.
Right.
But I think it's an important question from you. These results alone do not useful. If you can obtain some numbers, topologically this is the numbers for some finite groups, non-commuting of some finite groups, I think is not important. If you can obtain some results related to some properties of groups, it can be useful. But only obtaining these numbers, only these numbers for non-computing of some finite groups, I think it is not useful, and you must working about obtaining some properties according these topological indices for the obtaining some properties of finite groups. If you can do, yes, it is useful. If you can do not, I think that it is not useful for only obtaining these topological indices.
Yeah, I agree, Prof. In the process of getting the indices, there are lots of properties for groups and also the graphs that we should.
Let me explain. You know, we have two ways on topological indexes. So, firstly, we may see that what chemists actually, what the structure, what molecules they need these topological indexes. So, and this on this way, we can just simulate the molecule to a graph and see that is there any group for that structure. Of course, as Prof. Jamshid mentioned, symmetric groups are so important because many of molecules, they are symmetric. So it's easy. Of course, not so easy, but we can just give a simulation of the molecule to a special symmetric group and then find the topological indexes. So in this case, it's very applicable because it's coming from the chemistry. The second way is that to do something on groups. Of course, not only for these groups, we may extend for some other groups like symmetric and alternative groups. We know that for symmetric and alternative groups, it's a little bit difficult because we have to know the exactly graph. We have to know the degree of vertices. We have to see that what's the graph structure, but it can be done. So it's if we start with dihedral group, quasi-dihedral group, genus quaternion group is good, but we can continue for some special cases of alternative group or symmetric group. For example, I suggest for the symmetric group, Sn, when n is prime, is a special case. So for this case, we may also find something. So, you know, it depends on the application of topological index in chemistry and just vice versa.
Okay.
Sorry.
Yes, I think our time is up now. I hope there's no any other questions. Okay, then thank you very much, Prof. Samin, for a nice talk.
Thank you very much.